Hi guys. So I'll be explaining my project, the 3D Ken Burns effect using dual pixel sensors. Uh, yeah. So what is a 3D Ken Burns effect? 3D Ken Burns effect is an effect by in which you uh, by a clever use of pan, tilt, and zoom, you kind of focus on an object and move closely towards it to give the user a 3D experience. So Ken Burns effect, as it originated by a man named Ken Burns, was that given a 2D scene and an out, I would say, final crop of that 2D scene, the Ken Burns effect used to zoom into that 2D scene to give an experience of, I would say, focus on an object and kind of a cinematic experience. So 3D Ken Burns effect is similar, but you make sure that the experience is 3D, such that the users kind of get an immersive view and a 3D view of the scene just from a monocular image. So one of the pivotal works in the area of 3D Ken Burns effect was by Adobe, wherein they used deep learning uh, and an extensive pipeline to build the 3D Ken Burns effect from a monocular image. The way they do it is they first do depth estimation using a normal depth estimation network, then use a segmentation network to refine the depth, and then a depth refinement network to get accurate depth estimates. Once that is done, they convert the entire scene into a point cloud and then render a novel view. And as you can expect, this novel view would have some areas of stretchy depths and stretchy artifacts. And they fill those using immersion painting to kind of get a good novel view and blend in those stretchy artifacts. So this is kind of the entire pipeline wherein given an image and a depth, they first convert it into a point cloud, extend that point cloud to render a novel view, and then in paint that the stretchy artifacts in the novel view. Uh, and they do this repeatedly until they get a sufficiently extended point cloud. And these are the effects. So the effects are really cool because for even areas where depth is large, the entire scene that is generated is really fascinating. One of the drawbacks that I kind of think of this method is that it has three deep learning networks to estimate depth from a monocular image. And as it is depth from monocular image is an ill-posed task, plus this would be heavy computation and thus not suitable for mobile applications. So is there a way to get accurate depth from monocular views is something we would tackle here. So one of the answers that we have is dual pixel sensors, which we also kind of briefly studied in class. So what is a dual pixel sensor? So in the normal, this is on the left is a normal sensor and on the right is a dual pixel sensor where we split the green pixels into two such that we have an approximation of light field with just two lenses. So given a scene point which is in focus, you would still get the same image as that from a normal sensor. But all points that are out of focus, you would get a slight disparity, right? Because there will be disparity between the left image and the right image because you have now split the pixel into two. So that's why we kind of see a shift in these two images. And this is the entire concept behind how dual pixel sensors work. So one obvious use case that comes to mind directly is estimating depth because you now have a disparity estimate that you can approximate to build a depth estimation module. Another one that we did in light fields is to build an all-in focus image. So dual pixel sensors have recently been uh, I would say they're present in almost all uh, industry camera vendors, but only if the APIs they have exposed APIs by only Google and Canon. So all online datasets that I could find were either captured by a Google Pixel or by a Canon DSLR. So one of the pivotal works in depth estimation by dual pixel sensors came out of CMU, also in collaboration with Google and Adobe. Uh, so what they did here, so just to recap, the task here is that given a left image and a right image with a small disparity, give me really good depth estimates. So what they did here was they represented the entire scene into a multi-plane image where every plane is kind of an approximation of some depth, and they represented every plane with an alpha and an intensity channel. The final goal is to kind of compute alpha as well as the intensity channels. The combination of these alpha and the intensity channels would give you a defocus map that is an approximation of the depth, and the combination of the MPI layers in itself will give you an all-in focus image. So the observed image is calculated using the following equation, using the intensity channels, the alpha channels, and the K term here are the calibrated kernels for the specific lens. So this is done for the left image as well as the right image. I'm skipping some detail here because of the time constraint, but the observed image is calculated by using this equation. And once we have the observed image, we can then compute a loss between the computed observed image and the actual image that was captured, and we can then optimize on the alpha and the intensity channels to give us the right estimate of the alpha and intensity that approximate the scene at every level of depth or every image plane. So these are the results from the dual pixel sensors. They give really good approximations for depth in the scene. And how do they look when these depth estimates are incorporated with the 3D Ken Burns effect? So it looks something like this, which I think is really fascinating, or I would say it gives the right idea of the 3D Ken Burns effect, where the object that has the least depth is in focus while everything else is moving. Something similar in this example as well. So one, I would say, comparison that I wanted to bring up was the original depth estimation for this scene. It could not handle this image because inherently depth estimation by deep learning is a data-driven task, and there'll definitely be outliers or some sort of image uh, enhancements or image categories that the model might not be able to give accurate depth estimates. But using this technique, you can build an multiplane image for virtually any image and then bring out, pass that through the 3D Ken Burns effect pipeline and then get a really good view. Uh, so some sort of future scope in this area would be that the current depth estimation by dual pixel sensors is not at all real time. It takes almost 2 hours for every optimization. So if we want to have a mobile application that accurately does it, we would need to have something that is in real time. So probably deep learning could be the way here, wherein you get a single inference in real time. And because even though this would be a data-driven task, dual pixel sensors inherently have disparity. And so that disparity can be modeled much easier in a much easier fashion by deep learning rather than directly using monocular images and estimating depth. Second is that so was one task in which depth is used, the 3D Ken Burns effect. There are many other downstream tasks that uh, use depth estimates, and all those tasks can be explored by using dual pixel sensors because dual pixel sensors are something that can be easily deployed on mobile phones, and then we can have real-time applications using dual pixel sensors. So that is definitely something that needs to be explored. So this is my overall project. Uh, Thank you for listening.